everyone, this is Mrs. Jackson, and this is Chapter 1, Section 4, Part 1. This section is all about arithmetic sequences and series, and the textbook put it in Chapter 1, I think because they really didn't know where else to put it. But it is certainly related to functions, specifically linear functions. One thing to note real quick is arithmetic. Arithmetic is a noun, and that is when you do basic math, add, subtract, multiply, divide. But when you make that word an adjective, in this case it's describing the word sequence here, it's pronounced slightly different even though the spelling is the same, so it kind of is pronounced like arithmetic sequence. So just wanted to point that out. Okay, so what is an arithmetic sequence? It is a list of numbers. I guess it could be a list of algebraic expressions as well that has a constant difference between consecutive terms. I'll just shimmy in here, between terms. But you know what I mean, it's side-by-side terms. And the common difference is this constant difference that we're talking about. So I don't care if you call it the common difference or the constant difference, doesn't matter to me, as long as you know how to use it in a formula. And we have a variable that we describe this constant difference or common difference, and it's D for difference. So let's take a look at an arithmetic sequence. And I've got a list of numbers here on the left. Zoom in on there. And the first thing, and why it's related to functions at all, is because we're going to look at these numbers here as the output. So that's the output. And our input, we're actually going to call n. And n is used, I'm going to make a table now to describe this more as a function. N is used to describe the position of the number in the list. And there are natural counting numbers. So n1, 2, 3, 4, 5, ... up to n. And our output f of n, so function, the output depends on the positioning in the list. The very first one is -3, 2, 7, 12, 17, ... f of n. Okay, so you kind of have to take it for a test drive and see what's happening between consecutive terms here. And hopefully you can tell right away that there is a pattern. And the pattern is from -3 going up to 2, we're adding 5. And from 2 to 7, 5, 7 to 12, 5. You can see it's the same number. And so this is our common difference here, D. So let's break down the numbers and see how the sequence comes together in its pieces and parts. And then from that, you can see how to build the formula for an arithmetic sequence. I don't believe in memorizing the formulas. I want you to know where it comes from. All right, so let's start with the very first number in the sequence. F of 1 is the first place number, and that is -3. F of 2, we start with a -3, and then we're adding 1, 5. Actually, I think what I'll do is I'll just write, we're adding 5, and then below this, I think I'll say equals -3 plus 1, 5. You'll see why in a minute. And that output is 2. Now we're going to go to f of 3. And again, we start out with -3. And now you can see we're adding 2 5s to get up to 7. So I'm going to write +5, +5. Repeated addition is really multiplication. So I'm going to say plus 2 5s. And that gets us up to our 7. F of 4, whoopsie, somehow my color changed. f of 4. We're starting out with our -3, and now we're adding 3 5s. So I will write 1, 2, 3. So we're starting with -3, and we are adding 3 5s. I'm going to represent 5 plus 5 plus 5 as 3 times 5. And finally, f of 5. We're starting with the -3, and we're adding 4 5s. And I'm going to put that as multiplication of 4 5s. And let me just finish up here. So f of 4 is our 12, and f of 5 is our 17. Well, there's certainly a pattern here that we can create a formula from. The reason why we'd want to create a formula, by the way, is so that we could find f of 50 or f of 100. We wouldn't want to spend all the time it takes to keep this pattern going for that many numbers. So we'd like to be able to just use a formula to find that 50th or 100th number in the sequence. So basically you could see a pattern coming here, f of n. It's always going to start out with that first number in the series, which we would list as, the first number in the sequence, which we would list as f of 1. And you can see we're multiplying this number 5, this common difference, by something. Now let's see what that something is. In every case, well, first of all, for f of 1, n equals 1, there is no 5s. For n equals 2, there was 1 5. For n equals 3, there's 2 5s. 4, 3 5s. So you can see there's certainly a pattern here. In every case, we're going to multiply the 5 by n minus 1. We're 1 off, if you will. So let's use this as an example. Let's do that f of 50 as an example. Why would we want this formula? So we could put in our -3 plus 5 times 49. And I'm going to take my -3. Now I'm going to view, instead of viewing this as 5 times 49, I'm going to view this as 5 times 40 plus 9. That way I can do the math in my head. So 5 times 40, I'm going to use the distributive property. 5 times 40 is 200. 5 times 9 is 45. So the 50th number in the sequence is going to be 245 minus 3, which is 242. That's certainly easier for us than writing out all those numbers. All right, let's try it again on a new sequence here. So first thing, we make a table. So n, try to make straighter lines here, f of n, and our first number, 2, 3, 4, how many numbers I have? 5 again, ... n. So our first number is 4, second number is 20, third number is 100, 500, 2500, ... f of n. All right, take it for a test drive here, see if you can see a pattern. From the first to the second, we're adding 16. From the second to the third, we're adding 80. Right away, you can see we're not adding a common difference. Okay, even by the second, between 2 and 3, you could see that. What's happening here, though, is we're multiplying by 5 each time. And I'll represent that this way. So right away, this is not arithmetic. So I just wanted to point out an example that is not. When we have a common multiplier, these are multiplying now, we call this a geometric sequence. So I'll show me that in here. Geometric sequence is related to exponential functions. And we're going to study that in another chapter. But it's okay, we might as well take a look at breaking this down now and see exactly what things look like here. So I'm going to write my f of 1 equals 4. F of 2, I'm going to start with my 4, and then I'm going to multiply it by 5. F of 3, I'm starting with my 4, and I've got 2 5s now. 5 times 5 to get up to f of 3. So I'm going to write that as times 5 times 5. And below that, I'm going to rewrite that as 4 times 5 squared. 5 times 5 is 5 squared. F of 4, I'm starting out with my 4, and now I've got 5 times 5 times 5. I've got 3 of these. So I'm going to write that as 4 times 5 cubed. F of 5 equals 4. This time I have 5 times 5 times 5 times 5. I've got 4 of these. And I'm going to write that as 4 times 5 to the 4th power, etc., etc. Why don't I, oops, I'm going to change that color here. So that's an output of 4, an output of 20, an output of 100, an output of 500, and an output of 2500. All right, so this pattern doesn't have repeated addition like the arithmetic sequence does, but we can still write a formula here. You can see that our output, f of n, every time we start with the first number in the sequence, f of 1 in this example is 4, and we're multiplying it by a base. And we call in a geometric sequence this as the common ratio. So we use an r, and it's raised to some exponent, this exponent. When n equal 2, the exponent was a 1. When n equals 3, the exponent is a 2. When n equals 4, the exponent is a 3. So you can definitely see a pattern here. And that exponent is n minus 1. Every row, it's 1 off n. And so that's a geometric sequence. More to come on that in a future chapter. Okay, so hope this video helps. We looked at what is an arithmetic sequence, how to spot one, and where a formula comes from, breaking it down into its pieces and parts in order to write a formula. And that formula is used to find a number farther out in the sequence and not have to spend too much time doing that. Okay, hope this helps.